Okay, we're going to continue our discussion on chapter 4. So here we have complex zeros and the fundamental theorems of algebra. That's what we're going to look at. It can be shown that if a plus bi, you guys remember when we talked about the complex number before? A plus bi was a complex number. If a plus bi is a zero of our polynomial function with real coefficients, then so it is conjugate. So if a plus bi is a zero of a polynomial, we want to recall now that a minus bi also would be the zero of that same polynomial. So conjugate zero theorems. Let's take a look at this. Find a cubic polynomial function p in standard form with real coefficient having 3 and 2 plus I. So it's given that the zeros would be 3 and 2 plus I. If 2 plus I is one of my zero, its conjugate also must be another of my zero. Okay, so I would have 2 minus I also would be my another zero. So it looks like we have 3 is 1 0. So if 3 is a 0, a factor of that would be what then? That would be x minus 3 must be one factor of that polynomial then, right? That's what it says, x minus 3. If 3 is one of my zero polynomial, then x minus 3 must be one of my factor, right? Because if I solve for x minus 3, what do I get? X equal to 3. That's my solution, or 0. If 2 plus I is one of my zeros, then x minus 2 plus I must be one of my factor. Since I know 2 plus I is one of my zero, 2 minus I must be one of my zero, then my other factor would be x minus 2 minus I. So we see where this come from. So if I were going to solve for this, this would be my polynomial here, right? If this were equal to 0, if I solve the first one for x, what do I get? X minus 3 equal to 0 means x equal to what? 3. That's what it says. It says one of my 0 is 3, and so on. If my other factor is x minus 2 plus I, if I solve this for x would be plus 2 plus I, and 2 minus I. These are my other zeros. So what I need to do now is to kind of remove the parentheses here. So if I distribute this minus here and distribute this minus here, I get x minus 2 minus I. Here would be x minus 2 plus I. Negative would be plus. And then you can see this would be these two terms here. Its product would be x squared minus 4x plus 5. Could use the difference of a square here also if you didn't want to multiply term by term. This would be like a minus b times a plus b would be a squared minus b squared. This would be your a, and this would be your b. This would be your a, this would be your b. And look at this as a minus b times a plus b. That would be a squared minus b squared. A squared would be x minus 2 squared minus b squared. B squared is I. So remember what I squared is equal to, right? What's I squared, anyone? Negative 1, right? Every you see I squared, you replace it with negative 1. And that's how you get this term here. Or you could multiply term by term here. And then when you distribute x minus 3 by this polynomial, you get your p of x here. Okay, so we get that one. So this would be a minus, I could write this as, this term here could be a squared minus b squared, right? This would be x squared minus the 2ab would be 4x plus b squared is equal to 4, okay, minus I squared is minus 1. So this would be plus 1, right? These two give you the 5 that we have here. And these terms here would be right there. So that would be kind of like a shortcut. If not, you have to multiply term by term. All right, so we all know how to do this. So p of x would be x cubed minus 7x squared plus 17x minus 15. That is my polynomial. Multiplying the polynomial by any real non-zero constant a will also yield function satisfy the given condition. So if I put the a here, that also would be like a general form of that polynomial. To find that for part B, it says find a polynomial having a 0, 3, and 2 plus I that satisfy this condition. Now this condition would help you to find that A. Got it in the general form. So it means if x is equal to negative 2, y is equal to 4. That's what it means. So in this case, p of negative 2 is given to me equal to 4. So that's all I have to do is just substitute the values for each x negative 2, for each y 4, and then simply solve for a. And you all can do that if I give you enough time. So a would be equal to minus 4 over 85. So therefore, my p of x then would be, instead of a, I'm going to put minus 4 over 85 times what we calculated before. If I distribute this, I would get my p of x in that form. And we can easily check our graph using our graphing calculator. Every function defined by a polynomial of degree 1 or more has at least one complex zero. So if p of x is a polynomial with degree of 1 or more, then there is some number k such that p of k is equal to 0. P of x would be equal to x minus k times the quotient. So let's take a look at the number of zero terms. The function defined by a polynomial of degree n has at most n distinct complex zeros. So for all complex zeros of given that 1 minus I is a 0. So in this case, we have p of x equal to given to us as that. So if you look at the remaining zeros are found by first division, original polynomial by x minus 1 minus I. So in this case, if I go ahead and divide 1 minus I by this polynomial here, because this is a factor, the remainder would be equal to 0. Okay, the steps would be exactly the same as when we looked at the real numbers. You bring down all the coefficients here. 1, negative 7, 18, negative 22, 12. And then we're dividing that by 1 minus I. So your k is 1 minus I. You bring 1 down here, same steps. You multiply 1 by 1 minus I, you replace it here, you add them up. You multiply 1 minus I by minus 6 minus I, you place them here, you add them up, and so on. Just recall that every time you, in your calculation, you get I squared, you replace it with minus 1. Okay, next, divide the quotient from the first division, x minus 1 plus I, because remember, if 1 minus I is a root, 1 plus I also will be a root. As you can see, if you divide that, same steps, and then you would see that the remainder also would be equal to 0. So the zeros of x squared minus 5x plus 6 are 2 and 3. So the p of x would be equal to x minus 2 times x minus 3 times x minus 1 minus I, x minus 1 plus I. So therefore, the 4 zeros would be 1 minus I, 1 plus I, and the remaining of those would be the 2 and 3, because that was factorable, okay? We could factor this portion here to x minus 2 times x minus 3, and x minus 2 give me x is equal to 2. That's one of the roots here that we find here. X minus 3 equal to 0, that give me x equal to 3. And that would be my other root. And we can easily again confirm our result using our graphing calculator. You can see where would be the zeros here on the graph. This would be an interesting case where you have multiplicity of the zeros. If you have more than one zero, so in this case, if I have a p of x is equal to this polynomial, when you factor this, so for the x leads to the single zeros because there's no exponents here. However, for x plus 2 square, leads to have zeros at minus 2 in more than one place. How many places? 2 places. You have 2 multiplicity, 2 of them. For plus 1, x minus 1 equal to 0, that gives me 0 is 1. So how many places we should see in this case? 0. 3 places. The multiplicity of that would be 3. Okay, so the exponents will tell you how many times those zeros repeats there. So find a polynomial function with a real coefficient, least possible, and zeros of a 0 of multiplicity of 2, and a 0 of I of a single multiple. So in this case, okay, so one of my zeros is I, so the other one must be I minus. Remember, when 1 0 is I, the other one was its conjugate, so it would be minus I. So both I and minus I would be my other factor would be x minus I, x plus 5. And then for 2, it says for 2, the multiplicity of 3. There you go. A 0 of multiplicity of 2. So that means we have x squared. Because x equal to 0 is one of my 0, right? So multiplicity of 2 then would be x squared. And then we have my other 0 is 2 with the multiplicity of 3. So it would be x minus 2 to the power of 3. So 1 0 would be with the multiplicity of 2, so it would be x squared. 2 has a multiplicity of 3, so it would be x minus 2 cubed. And then we have I. So because we have I as 1 0, the other one would be x minus I and x plus I. Okay, so if you multiply all this together, then that would be my polynomial. So we should be able to read the number of zeros and the number of zeros that we have, and copy our polynomials based on that. So again, this would give me what we just talked about, where my graph going to intercept at what axis. If you look at the graph of this, you can easily see that, confirm that what we have here, where we have the zeros appears to be at x equal to 0 is right here. At x equal to 2, that would be my other zeros right there. Now, this is something that you may want to put it on your summary sheet, graphs and multiplicity. The graph crosses the x-axis at k and 0 if k is a 0 of multiplicity lines. The graph is tangent to the x-axis at this point, k and 0, if k is a 0 of even multiplicity. Okay? If it's odd, we look like that. The graph crosses and is tangent to the x-axis at this point if k is a 0 of odd multiplicity greater than 1. Okay, so kind of wiggles at this point k. So let's take a look at this polynomial. We're going to sketch this polynomial. P of x equal to minus 2 times x plus 4 squared times x plus 3 times x minus 1 to the power of 2 by hand. The dominating term would be minus 2 times x to the power of 5, right? This is x to the power of 2, this is x to the power of 1, this is x to the power of 2 again, and then we add them up, we would get x to the power of 2 times x to the power of 1 times x to the power of 2, they give you x to the power of 5. So the end behavior, remember from the previous section, will rise on the left and fall on the right. So these are the facts that you definitely want to write it on your summary sheet, right? If it's odd, that's how would be the end behavior of that. Because minus 4 and 1 are x-intercept, so minus 4 is right here. This would be one x-intercept, x plus 4 equal to 0, x equal to minus 4, that would be 1. The next one is x minus 1 equal to 0, x equal to 1. So if minus 4 and 1 are the x-intercept, exponents here is even, the graph will be tangent to the x-axis. However, for the other one, x plus 3 equal to 0, x equal to negative 3, at this point, the exponents here is odd. So the graph will cross the x-axis at this point. And the y-intercept would be if x equal to 0, solve for y, we can find that easily. If x equal to 0, substitute 0 here and solve for p of x would be minus 96. So these are all the information we need to sketch a graph. Let's take a look. As you can see, the x-intercept would be minus 4 and 1. It would be minus 4 and here's 1. And as you can see, the end point is shown here. And then the graph going to intercept at this point 0 and minus 96. If x equal to 0, y is equal to minus 96. This area here, we cannot really determine the exact location of this part by what's given to us. However, if you look at the graphing calculator, you can see we're pretty much very close to what the graph looks like, except this portion here. But pretty much we got the graph by the information that we have here. We sketched the graph of this polynomial. Let P of X equal to an times x to the power of n and all the way to a of 0. So this is how you write the P of X. And where a of n, the leading coefficient here is not equal to 0, of course, and a0 is not equal to 0. Defined a polynomial function with integer coefficient of P over Q. Again, this is something else that you want to put on your summary sheet, you guys. If P over Q is a rational number written in its lowest term, and if P over Q is a 0 of P of X, then P is a factor of the constant term A0, and Q is a factor of leading coefficient A0, AN. This all makes more sense when we look at it as an example. Let's take a look at this one. Find all rational zeros of this polynomial. P of X equal to 6, x to the power of 3 minus 5, x to the power of 2 minus 7x plus 4. Okay, so in this case, we're going to determine which one is the leading coefficient. The leading coefficient here is 6, and the constant is 4. These are the two terms that you want to look for, because if you recall, P, when you're finding all these P over Q rational zeros for the lowest term, P is a factor of the constant. So this would be my P. Factor of 4. What are the factor of 4? Would be 2, right? 4, 1. These are all factor of 4. And then Q would be this leading coefficient, the factor of this leading coefficient. So we determine, look at the constant and the leading coefficient. So all the factor of P then would be plus and minus 1, plus and minus 2, plus and minus 4. These are all the possible factor of P. What are all the possible factor of Q, the leading coefficient? Plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. So, as a result, any rational zero of P of X in the form P over Q would be plus and minus 1 over 6, 1 over 3, plus and minus 1 over 2, 2 over 3, 1 over 1, 4 over 3, 2 over 1, 4 over 1. If you reduce that, you would get one of these. So you get like 4 over 6. That would be reducing to 2/3. It's already here. So these are all the possible ones. So if you evaluate P of X at these points, you can see that P of X would be 0 at like x equal to 1/2. P of X would be equal to 0 at x equal to minus 1. P of X would be equal to 0 at x equal to 4 over 3. So that means from that table, we can see -1, 1/2, and 4 over 3 are rational zero of P of X. These are the factor of that polynomial. The first factor would be x plus 1 then. The next one would be x minus 1/2, and the next factor would be x minus 4 over 3. So we can find that A, leading coefficient of P of X is 6. So let A be equal to 6. So we can go ahead and actually find our polynomial that way. Would be 6 times these 3 factors that we find. You can distribute that. I'm distributing 6 as 2 and 3, and we distribute 2 with this one, so you eliminate this 1/2, 3 with this one, so you eliminate this 3. So this would be my P of X. That would be my polynomial. Okay, so this would be another example here. We have P of X is given to me as this. We want to list all possible rational zeros here, and for rest for part B and C. Now would be a really good time to pause the session and see if we can come up with all the list of all the possible rational zeros. So if you're watching this later at home, I suggest you pause and see if you can get all the list. All right, so let's take a look. In this example here, for part A, A0 is equal to 2. So all the factor of that would be plus and minus 1, plus and minus 2. A4 is equal to 6. All the factors of that would be plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. So the possible rational zeros would be P over Q. So you just go down plus and minus 1. When you reduce those, it would be one of these, plus and minus 2, plus and minus 1/2, plus and minus 1/3, plus and minus 1/6, plus and minus 2/3. Now, in this example, they're asking us to look at the graph of the function. You put the graph on your calculator and see which one of those would be a possible zeros there, okay? From the graph, the zeros are, look at the graph. The zeros are no less than minus 2. They cannot go below minus 2. This is minus 1, this is minus 2. So they cannot be below minus 2. There's no zero here. Your graph is not going to pass this x-axis below -2. Also, your graph is not going to pass this x-axis right after 1. Okay, this is 1. There's nothing after 1, right? So this means that 2 is not a 0. Also, -1 is clearly is not a 0. So they just want to know, eliminate which one are not 0. So we can, just by looking at our list here, we can exclude some of these. So the x-axis at point -1 and 0 would be there. So you want to show that 1 and -2 are 0. And we can easily do that now by using the synthetic division. If I divide that using synthetic division, we're going to pay attention to our remainder. If the remainder turns out to be equal to 0, it means that is a factor. Well, it is in this case. So as the other one, -2. Now, this would be my quotient here, 6x squared plus 1x minus 1. If you solve this, you would get the other zeros, because that is factorable. Okay, this would be x minus 1 times x plus 2, and there it is. These are all the zeros appears right now. This would be the next thing that you want to know, Descartes' rules of sign. Again, you definitely want to write this, include this in your summary sheet. And it's a pretty simple concept here. Let's read through this and look at some example, and the example would make a lot more sense here after we read through that. Let P of x define a polynomial function with the real coefficients and non-zero constant term. The term is descending power of x. So we just write it in that order, standard form. Part A. Now this is what you want to write in your summary sheet. The numbers of positive real zeros either equals the number of the variation in sign occurring in the coefficients of P of x, or is less than the number of variations by the positive even integer. Okay, for part B, the number of negative real zeros either equal the number of the variation of sign occurs in the coefficient of P of minus x, or less than the number of variation by the positive even integers. Okay, let's keep all this in mind, and then we're going to go ahead and look at the examples now. Now, let's take a look at this first example. We want to use this to take a look at this P of x. P of x equal to x to the power of 4 minus 6x to the power of 3 plus 8x to the power of 2 plus 2x minus 1. The first thing you do, you just want to write this in order, which is already in order. Basically, go from left to right and see which of these would change sign. Okay, so the sign of x to the power of 4 is what? It's positive, right? Going to the next one, it changed sign, right? From positive goes to negative. So I'm going to mark that one change sign occurs right there. From the second one to the third one, again change sign. So I'm going to make a note here that the second term also again change sign. Does it change sign on this one? No. So we don't care. But the last one, it does change sign from plus to minus again. So it changed sign for the third time here. So by Descartes' rules of signs, f has either 3 or 3 minus 2, which is 1 positive real zeros. Let's just start predicting how many zeros we have. Either we have 3 because it changed 3 times, or remember it says 3 minus the even. Let's go back to the property here. It says either is positive or less than number varies by positive even integers. Okay, positive even integers is 2 here, right? So either 3 or 3 minus 2, which is 1. So these are the possibilities of 0 that we could have here. Now, these are how many positive integers positive 0 we're gonna have. In order to find how many negative zeros you have to evaluate p of minus x. Now, it's pretty obvious how to find p of minus x. That's all we do, just substitute for each x minus x into our p of x function here. So everywhere we have ECX, you're gonna put minus x and kind of evaluate that. Okay, the first one would be the same because the exponent is even. So this would x to the power of 4. Now this would becomes minus because the exponent is odd. So that would be minus, and minus would be plus 6x to the power of 3, and so on. Now when you do that, you notice that the first to second doesn't change sign. Second to third doesn't change sign. The only time you change sign would be from third to fourth. It's only one time. Since there's only one variation of sign in sign, p of x has only one negative real roots. So we want to determine the positive number of. We want to determine the possible number of positive real zeros and negative real zeros for this. Okay. So in this example here, let's see how many times it changed sign. So in this case, we have plus here, p of x. This would be 1 time, changing sign here, 2 times. Does not change sign. It does change sign here. Has 3 variation in sign. If you ignore the missing x to the power of 3, then p of x has either 3 or 1. 3 minus 2 would be 1. Positive zeros. To find a number of negative zeros, you need to find p of minus x. You substitute for each x negative x, and then we do the same thing here. The sign doesn't change here. The only time signs change here from negative to positive right here. Here, positive to negative changes right here, and doesn't change here. So it has 2 variants in sign. So p of x has either 2 or 0, because 2 minus 2 would be 0, negative signs. All right, the next thing is boundless theorems. Let p of x define a polynomial function for degree n is greater than or equal to 1 with the real coefficient and with the positively leading coefficient. If p of x is divided synthetically by x minus c. Now, this is another thing that you want to write in your summaries here, you guys. If c is greater than 0, and all numbers in the bottom row of the synthetic divisions are non-negative, then p of x has no 0 greater than c. And then for second is if p is less than 0, and the number in the bottom row of the synthetic division alters between the sign, then you can say that the p of x has no 0 less than c. Again, every time you look at the example, with these terms will make a lot more sense. Let's take a look at this example here. We want to show that the real zeros for p of x, if p of x equal to 2x to the power of 4 minus 5x to the power of 3 plus 3x plus 1, satisfy the following condition. Okay, basically we need to set up the synthetic division and look at it. So if you look at the first one, it says no real 0 is greater than 3, or for part B, no real 0 is less than minus 1. Now in this case, c is greater than 0. If I go ahead and use the synthetic division, dividing it by that 3, you notice that in this example, there's no changes. So all are negative, no real 0 greater than 3. And for the part B, if you look at the synthetic division, you see the sign alters between plus and minus, plus, minus, plus, minus, plus. So the number alters in sign, so no 0 less than minus 1.